Welcome back. Today I would like to discuss another type of voltage scaling technique, that is multi-level voltage scaling. So in multi-level voltage scaling technique, as you know already, it uses more than one power supply, but the selection of power supply is depends on the amount of delay provided by the subsystem. You know, from the delay derivation, the relation between delay and VDD is inversely proportional. If the supply voltage is less, high delay we can expect. If the supply voltage is high, low delay we can expect. So in multi-level voltage scaling technique, the subsystem which provides low delay, they are operate at high VDD. Which provides high delay, they are operate at low VDD. So that ultimately for the entire system, the power consumption can be reduced. In general, in a system, from the input to output, the paths are divided into two categories, critical and non-critical, based on the delay. In general, in the critical path, you can expect less delay, whereas in non-critical paths, high delay we can expect. So, in case of critical path, high VDD gates are used, whereas in the non-critical paths, low VDD gates are used. But in this type of voltage scaling technique, you have to face the many problems or many challenges you have to face. The challenges like interfacing, voltage scaling interfacing, placement of converter, floor planning, routing and placement, static timing analysis, power up and power down sequencing, and clock distribution. Let us see one by one. What is the interfacing? Interfacing means providing a connection between one circuit to the another circuit in general. But here the problem is, since the different subsystems are work at different power supplies, their voltage ranges for logical 1 and logical 0 are different. So if they are in the acceptable range from one voltage domain to another voltage domain, there is no problem at the end result. But if they are not in the acceptable range, you can get the error results at the end. Suppose if you see in this example, the first gate is work at the low VDD, whereas the second gate work at high VDD. So with some particular value of the output value of low VDD gate, sometimes may short circuit the high VDD gate, so that the static current is very high in the high VDD gate and the static power consumption is large. To avoid this, a proper converter you should place in between these two voltage domains. Therefore, in the literature we have two types of converters: high to low level converter or low to high level converter. Let us see high to low level converter symbol, and its internal diagram is like this. The first one represents high to low level converter symbol. It converts the voltage levels from high voltage VDD domain to low voltage domain. Its internal diagram, if you see, there are two gates, two inverters connected in cascade. So totally it works as a buffer. That means whatever the value you applied at the input, the same value you can get at the output, but their voltage levels are different. The input is from the high voltage domain, but the output is to the low voltage domain circuits. Similarly, if you see low to high level converter, this is a symbol for low to high level converter. Okay, that means its input is from the low voltage domain gates and output to the high voltage domain circuits. but it works at different voltages. One is VDDL and another one is VDDH. Its internal diagram is like this. The internal diagram includes a dual cascode voltage switch logic. A dual cascode voltage switch logic. That means it includes a differential amplifier or a differential circuit and positive feedback circuit. Let us see whether it gives the same output or not. Suppose if the input is logic 0, the output of the first NOT gate is 1, whereas the output of the second NOT gate is 0. With reference to these output values, the corresponding M1 and M2 transistors are on and off respectively. Since M1 is in on, therefore the M4 PMOS goes to on state. Since because of the feedback connection, the M3 goes to off state. So that before the final NOT gate, the value is logic 1. Therefore, the output out H is logic 0, but the voltage value with reference to high voltage domain. Like that, it converts low voltage domain values to high voltage domain values. So these are the two types of converters you need to use to get the compatibility between different voltage domain circuits. Next thing is floor planning, routing and placement. As you know, here we have different voltage gates are used and converters you have to place. Different power supplies are there, power supply rails. All these must be properly placed, otherwise malfunctionality you can see at the final. And another one is let us see, this is the one of the way how the subsystems are placed in a chip. So usually the subsystems or logic gates are arranged in the form of rows. If you observe, the first row consisting all the gates which are operated at high VDD, whereas the shaded one represents low VDD gates. This is also low VDD gates, and these are high VDD gates. Like that, the gates which operate at one power supply, all those gates should be placed in a one row in order to avoid the proper connection. So see here, the vertical ones represents the power supply rails, say VDDH, VDDL and VSS. Similarly, VDDH, VDDL, VSS. Okay, so this dark one represents a joint between power supply rails to the gates which are placed in the VDDH row. And similarly, so these shaded rows are the low VDD gates. They are connected to low VDD power supply rail. So properly you need to place all the circuits. And static timing analysis is, if single voltage source is used, it is very simple to analyze the timing. But the multi-level voltage technique uses many voltages, so that definitely you need to accept EDA tools in order to optimize the timing analysis. And another one is power up and power down sequencing. Since different types of power supplies are used, all the power supplies may not be switched on or off simultaneously. If you do like that, what happens is a power supply glitches are occurred. Because of glitches, you can get the error results at the end. Okay, so proper power up and power down sequencing you need to maintain between different power supplies to avoid these glitches. Another problem is clock distribution. You know, the purpose of the clock is to get the synchronized operation, but the clock source is at one end of the system, but all the subsystems needs the clock signal, but they are not at equal distances from the clock source. So therefore, the clock is unable to reach simultaneously to all the subsystems. So therefore, you can't get the simultaneous operation between all the subsystems. So to avoid this, proper clock distribution has to be maintained. Then only you can get the synchronized operation. So these are the different challenges with reference to multi-level voltage scaling technique. Okay, thank you. In the next class, we can see another type of voltage scaling technique, that is dynamic voltage and frequency scaling.